Hi all, welcome to the session. So about today's bootcamp, like it is related to EKF-based SOE estimation. So maybe in the earlier webinars or the bootcamps, or you might have heard like Kalman-filter based SOC estimation, SOH estimation, but there is some other term called like SOE estimation, which is a parameter of the battery itself. So we will try to explore like in the concept of like SOE. Okay. Yeah. So first, like we'll try to discuss about the agenda. Okay. Like what all the points we are going to involve. Okay. And then like we'll discuss about uh, the script part and everything. So I'll just quickly let you know the agenda. That we will start with a basic introduction to the Kalman filter. So I'll just quickly cover the steps involved in it, like what are the steps involved, and like how it can be useful for the implementation. That we'll discuss, and we'll discuss more on the concept of SOE and the energy. And later we'll try to bring some a relation between SOC and SOE. Okay, so like both are different terms, but how they are like related when it comes to like estimation side. So that difference we can observe. Later, a mathematical modeling of the SOE in the state space with a Kalman-filter algorithm. So here I'll try to describe some like mathematical models, and we'll showcase the scripts like which has been built. So and we'll also try to run some test cases like for the standard current profile. And later we will discuss some basic results, like what the results we got. Okay. Yeah. So that is the agenda like of today's bootcamp, and that what we has been set. Yeah. Sure, guys. Like we'll continue with the session. Yeah. And whatever the content we discuss, the agenda. Yeah. So first, I will start with like a Kalman filter. So like if many people started working on this part, like they might have heard like many Kalman filter family like UKF, EKF. This is like a simple linear Kalman filter. Again, like there are AUK, EKF, UKF, and Kubecha Kalman filter. Like there are many more. So, but when we talk in a general, like it defines only these steps. Okay. So only let's say like people ask that what could be the difference between like KF and the EKF, right? So the thing is that like when the system is like the linear, then we make use of this Kalman filter, simple Kalman filter. And when there is a system is having a non-linear behavior, then we introduce like EKF or UKF applications. Okay. So in terms of maths involved, right? So here linearization of your like states, that matters a lot when it comes to like application of EKF or UKF. So there are different methods like Taylor's, the Jacobian methods will be used. And even let's say like AUKF, okay, adaptive extended Kalman filter. So there, like we may use, like not we may, like we are going to use the dynamic noises process or the measurement noises. Okay, but in the simple Kalman filter, like we will just use like a constant values. Okay, even the like whatever the error we know that will be also updated like when we use the AEKF. So yes, so in the Kubecha Kalman filter, there are different methods will be used. D Cholosky method for the linearization. So yes, uh, but only the terms of for linearizing, for making some components has a dynamic nature, to capture the non-linearity behavior. So in that way, we make the changes. But when it comes to the steps, all it is same. Okay, you take any Kalman filter family, like it has the 3 steps, like or time update, measurement update. Again, within the time update or like within the measurement update, like what are they, right? So one with the Kalman gain estimation, update of estimate with the measurement data, and again like the state updates, predict the state. Okay, so and initialization will be done for this one time. So the steps will be remain same. Okay, yeah, that is the major difference with other family. So keeping it as a general, so I'll just try to like explain the across the steps as in general. Okay, so one with the predict step, one with the Kalman gain estimation, one with the state update. Okay, predict step, it is nothing but like you're predicting your state. Okay, here you are updating the state variables, you can say. So with taking the influence of your measurement data. Yeah, so these are like the basic steps. So how it flows, right? So that is like the most important thing. So we know these. Okay, right now you can leave about this equation. So you can see this equation, right? So this is nothing but your like state phase representation equation, right? Yeah. So we know that like here we are going to put all our state variables, and your A matrix can be like a process, like a matrix where you will be using it as a like conversion matrix. So where all your what you call the state variable related equations, like let's say like my application is a cell model. So the cell model, the process of the cell model will be involved here. Like even you take uh, the vehicle model, right? So that vehicle model will be involved in this A matrix, right? Yeah, and then there is a B to U, so where it contains the input matrix. So what exactly this U has an input matrix? That, like for example, like in my case, if I'm taking cell, right? Cell, if I influence electric current to the cell, like just as a like for discharging or charging condition, so it will affect the voltage of the cell, right? So in the similarly, if you take the other example of the car, right? So my final agenda of the car is to like say that what is the displacement of the car, like what is the position of the car. So if the position has to be disturbed, so what could be the input? The acceleration is the input, right? So similarly, like for the cell, current will be the input, and that is multiplied. So and then there is like noises. Okay, so you can call it as like process noises, the system noise, you can say. So again, in the noise there are different, so I don't want to touch this topic right now. Yeah, and then there is a process noise the process matrix. Okay, process covariance, you can see over here. So this represents the error in estimate. So error in estimate means error in your state estimate. Yeah, so this is, you can call it as like first step and second step, and this could be the third step in general. So when you want to start with the first step, you need these data, right? So these data can be initialized. You can start with any data, like within some conditions. Okay, you can start with as a initial data, like x naught and p naught. And once you like feed them here, you're going to predict your state and the process covariance. And then the next step you are going to do is Kalman gain estimation. So the Kalman gain requires the input of measurement noise and the input of process covariance matrix. Okay. So it takes the system noise. System is nothing but your cell you can take, and the measurement noise. So that is, you can call it as like a sensor noise. Okay. So it takes the input of both system noise and the measurement noise. Yeah. And it is going to give a value that is a Kalman gain, which lies between 0 to 1. Okay. So this 0 to 1 defines that, like, to which weightage I need to give. Like, either I had to give the weightage more on the system, that is your theoretical model, or the weightage has to be given more to your measurement data. Okay. So that will be decided by the Kalman gain. So that Kalman gain, again, you are taking it for state update on the covariance update. So where you can find these equations. So you are going to multiply the Kalman gain here. And this one you are taking it from the measurement. And this will be your predicted state. And you are going to take a cell data from your like measurement, and you are going to multiply with Kalman gain, and you are going to add with the predicted state. So finally, you are going to get an update. Okay, that can be used as a output state, even on the process covariance update. Yeah. So this can be taken as output, or if you want to run for the next case, this can be used as an input for the next round of estimation. Okay. So this initial state will be used only for initialization. Later, it cannot be used. So whatever the output you get from your state update and the covariance update, that can be used as a input for your predict step. So that is how the cycle of Kalman-filter works on. Yes. So yeah, I hope I made some clear understanding of this, how it works. So yeah. So with this, like, I'll just quickly go to the concept of SOE. So SOE, like, we might have like in the market right now, like SOA, SOC, state of charge, SOH, state of health. So these are like trending parameters. Like, has been a lot of research is also has been invested in this like, to bring a right SOC value and the right SOH value. Even the big players also struggling. Okay. So then there is a SOE. Okay. So this can be used like, what is the capacity left in the battery? And this defines your health of your battery. And this defines your energy of your battery. So as an application point of view, it will be used for range estimation. So you cannot say that you are going to estimate the range with the help of SOC. And if you try, the value you are going to get, it will be like not accurate one. Okay, I'm not saying it's wrong. It's not an accurate, because many people try to estimate the range through capacity, but it's not works well. Okay, so because there is some relation, so that we will discuss. And when we talk about like range estimation, so we have to go for like estimating the energy available at the battery. Yeah, that we will discuss. Yes. So like, yeah. So for the range estimation, like the SOE can be used because like you need to predict the, what you say, like the exact energy available at the battery, right? So that is the important parameter. Okay. Uh, yeah. So with this, like we'll start into the SOE. So energy, like if I want to define energy for the cell, right? So the area under the curve. So the curve is nothing but your voltage versus capacity. The voltage here, it will be OCV, and this will be the capacity. In all, it can be also like termed in SOC. Okay. Yeah. So the area under the curve, we define it as energy. Okay. So when you might have observed that uh, uh, yeah, when you might have observed that like when we try to charge, when we try to discharge the battery or the cell at different C rates at the different temperature condition, so the curve like it may appear in something like this, right? So at the end, like has the energy area which is between voltage and capacity decreases, so we are not utilizing the complete energy here. Yeah. So with this, like, yeah, just go to this one. So just to give an explanation on the SOE and SOC, and also like a question that why can't we use the SOC, right? So when I said about range, right, like how much kilometer it can be predicted from the from the battery, like whatever the energy it's available. It is because of, you can refer this calculation. Like you will get some hints. So I'll just put it over this one. So let's assume that like if you have 10 kilowatt hour of battery, just taking a small example, like a random example, like 100 watt and 100 volt and the 100 Ah as a capacity. So assuming that its SOC decreased to 50%, right? So it doesn't mean that it is having 5 kilowatt. As when the battery is fully charged, let's say that like the capacities of sorry, the energies of like 10 kilowatt hour, but when the SOC is decreased to 50%, it doesn't mean that the energy is like 5 kilowatt hour, right? So it will be still less because the voltage is not going to be same, right? Like when you can see like as example, like the voltage is going to be dropped at the different SOC points. So that influence like has to be included when we talk about like range estimation. So then you can like say that a good range estimation can be considered. Okay. So here at like 50% of SOC, the voltage is about like assuming 86.4. So its energy will be like 86.4 volt into 0.5 into 100. So it will be like still less than 5 volt. Sorry, 5 kilowatt hour. Right. So this is the way like how it has to be calculated. Like when we represent our energy in terms of kilowatt hour. So that is why like we cannot go with predicting the range with the SOC. The capacity based it doesn't work well. Okay. Yep. So and then like the SOE definition like it is nothing but like a residual energy of the battery. So it is divided into like two theoretical residual and residual discharge energy. So this can be obtained. The let's say like if you want to calculate how much energy is there like from the battery, right? You need to discharge the battery at very low C rate, at very low current, or like so that you will get this theoretical residual energy. Okay, the graph. And this like RDE is the energy that can be released by the battery when it is discharged to a cutoff voltage under some certain load condition. The current load cannot be a small, like it will be a some considerable value. So at some conditions, right? So when we talk about like estimating the SOE stuff, so we are going to do it for RDE. Okay, because when we are like taken the vehicle at the ground applications, like uh, we are going to draw the current on like the load which is applied, it is in at a considerable conditions. Sorry, not a considerable conditions, like a considerable value at certain conditions. So right now, like the SOE, like all the things, like we are going to SOE estimation will be done for this particular area, that is RD, residual discharge energy. So yeah, just to quickly explore like methods. Okay, so before going into the script, so what we have worked on. So just trying to give some methods. Yeah, so there are some direct calculation method, power integration method. Okay, you can just make a note of this definition. Okay, so the equation is also like pretty simple. Uh, when like when we talk about like Kalman-filter based, we are going to use the combination of like power integration method with the Kalman-filter. Okay, so like if you remember for SOC Coulomb counting, right? So we used to do like something like this, right? We used to write the equation something like this: I dt upon Q. So I dt is nothing but current. If you multiply with the time, it will become capacity, right? So we used to call this as an instantaneous capacity. And if you divide with the rated capacity, like then you can say that is the SOC, the state of charge is like. So similarly for SOE, at the denominator, you are going to put some the rated energy, and at the numerator, like you're going to calculate or estimate the instantaneous energy. Okay, by going this through this equation, like SOE t minus 1 integration of t. So I have to put some sign over here. Yeah. I dt, like here I'm going to put v into I. So this will become power multiplied into dt divided by energy. Okay. The trend of the graph will remain same as of SOC. Yeah. So this will be your like rated energy, and this will be of instantaneous energy. Yes. So next, this is your like equation, like power integration method. And there are similar methods like what we do for SOC, OCV methods. And this one is the model based filtering method, like where we combinationally using, or like we are going to use combination of like cell model with taking the influence of SOE and temperature. And for these, you can also use the SOC instead of SOE. It will also work. And then rest thing is that for the Kalman-filter thing. Okay. The same steps you are going to involve here, like predict, update. So only thing is that your initial state will be linearized through some uh, mathematical approaches, like such as like Taylor series, one of the linearizing method for the nonlinear system. Yeah. So I'll just quickly go to the, okay, these are some methods of estimation. You can just make a note. So yeah, now I will just quickly go to this cell model development. So these are the set of equations for the cell model. So in my model, I just used up to here, like 1 RC. You can call it as like Thevenin model. I haven't included like the script which I'm going to show, that I haven't included this influence of 2 RC. Okay, the second, not 2 RC, like I can call it as like second RC model. Okay, yeah. So these are some derived equations from this. Just you need to like apply the KVL rule, and you are going to get this equation. Later you can take it for the discretized form. So then once you get this equation, you can apply the state space and you can bring them into the state space. Okay. The one which you saw, that x is equal to x equal to ax plus bu. Yeah. So yeah, and then like I'll just go to my MATLAB. So I hope you can see the script. So don't worry about this test data. Like we still, like it is in a validation stage. Like I'm not saying that it is, this script is like completely tested and validation. So for some cases we have tested. So we have to still, it is in a validation stage. Yeah. So the initialization, like we are going to do that, the initial states, like which I was explaining, right? So uh, that what could be the, in my case, like the states are SOC and your like voltage, I can say the VR. So I have initialized with one has a SOC. So in my case, like I can call it as like 100% SOC. Okay. So you can initialize with any number and it will like converge to its true value. Okay, that is the beauty of the Kalman filters. Yeah. And you are initializing the error covariance matrix. Yeah. So yeah, the questions I will take it after the session. Okay. Yeah. So you can just put the questions in the chat box. Yeah. So where was I? Yeah. So here, like about the initial covariance matrix, like we have considered. So it is just like Gaussian value, Gaussian noise, or like random values, I can say, not random, like Gaussian values. So yeah. So again, like modeling initial like error covariance matrix itself is a big task. And then like initial uncertainty noise as input, and then initial measurement noise. So then you can put some Coulombic efficiency, but right now, like Coulombic efficiency will be used in a SOC, but I'm not using it, the SOC equation, so I'm not using this part. And then the capacity of the cell. So the capacity is of 2Ah. Okay, the cell is of 2Ah, and I multiplied with 3600. Okay, yeah. This the purpose of doing it to convert into the amp second. And then like I have some drive cycle currents. Okay, so I am using like FUDS current profile, and like you can also you like this is a standard current profile, and also like UDDS or BJDTS. You can see it some current profiles. Yeah. And then like I have the data of the observed voltage. You can call it as like the machine data and the time. So then the UKF loop. So initially, like when I say about the mathematical model of the cell, so which includes all your like RC parameters. So that I'm going to represent with the uh, polynomial equations. Okay. Yeah. So R naught, R1, C1, and the tau, which defines your time constant. So later, like the derivative is so sorry OCV, and then we put it in the H matrix. We call it as like observation matrix. So with the influence of this, like we will calculate the voltage across the RC circuit and then terminal voltage. So in the voltage across RC circuit, like we named it as like VR1, and then like in the estimation of terminal voltage, this is the equation. So yeah. So if you include 2RC, right? So then there will be one more that here minus VR1 is there, like V minus VR2. Like one more this kind of equation we have to like set it up. Yeah. Okay. And then like algorithm, that is EKF. So A, B matrix, and yeah. Yeah, the questions I'm getting in the chat box, I will just answer in the end. Okay. Yeah, just be patient. Yeah. So, and then about the EKF algorithm, like the A-B matrix are defined. So you can see this particular equation. So the one which I was mentioning, right? So V into time, okay, divided by energy. Right now it is V into time, the power, okay. And here I have to multiply the time. Sorry, time is already multiplied. I have to multiply current to make it energy. So unit should be matching, right? So you can see here the B matrix where I'm placed over here. So I'll just try to make it big so that it will be easy to see. Yeah. Sorry, I think it's too big. Yes. So you can see this B matrix, which is of V into T, and I'm multiplying the current. So then it will become like instantaneous energy accumulation divided by the rated energy. So all these has been defined in the above, which I was showing the initialization part. Yes. And then like you can see this part. Then the predict of the previous state. These are the steps. Predict step and the Kalman gain estimation, which is the second step. And then like state update. So Kalman gain is multiplied to this error. So error is nothing but your you observe minus like your ut of SO underscore SOE. So this is nothing but your terminal voltage from your theoretical model, and this is terminal voltage from your cell. Sorry, from your real cell, like which we get it from the sensor. Okay. Yeah. Basically, you can say it as like sensor data. So, and then like once you have this difference, you are going to multiply with the Kalman gain, and you further added with the predict step, and finally you got the state update. So this can be taken as output, both of these, and or you can like give it as an input for the next step. So yeah, so you can see like the loop of the Kalman filter has been running from 1 to 6,200 seconds. Yes. So it depends on like how much the data we have in terms of drive cycle. Yeah. So I have captured some data for 2 drive cycle, like, and I'm going to run here also. So right now, I think I have put the FUDS current profile. Yeah, this is my, sorry, terminal voltage versus time and the SOE. So it also have an influence of like region because of the standard drive cycle. So yeah, I'm not saying that it is the result what we got like 100% because it is still in a validation. So yeah, somewhat it is giving a trend like what is supposed to give. Yeah. So started with the initial as a like 100%. Okay. So if I try to give the different value, it will start with a different SOE. Just trying to put some random value. You can see. Okay, so I'll just go back to my PPT. So these are some like for BJ DST current profile. Okay, and this is the one which you saw, FUDS current profile. So just for the sensitivity checking, like I can increase the capacity. So let's make it like 4, 3.5 or so, anywhere you like. Yeah, just to showcase like how it behaves. Yeah. So if I make it as 1 as 100%, yeah, let me open the results. This one. Yes. So if I try to compare, yes. So the QM, okay, the energy has to be changed, right? So sorry. So if you change, it doesn't affect. We have to change as the energy because this is the term as the input. So what I'm going to change, I'll change it over here. So initially it was given of 2.6 EH. Okay, not 2. Yeah, let me make it comment. So yes, yes, Vijay Kumar, yeah, you're correct. So yeah, now you can see the influence, the final value for the SOE. Yes, guys. So I'll just go back to my PPT. So I'll stop recording.